Okay. All right, section 5.1. I want to get down with the section. We'll understand how to construct a probability distribution for a random variable. And today it's discrete distributions. With any probability distribution, there is always an associated random variable that basically takes on any possible outcome that the experiment affords us. And the nature of the random variable characterizes what type of probability distribution we're talking about, whether we're talking about a discrete distribution or a continuous distribution. We say a random variable is discrete if it can only obtain or be assigned specific values, like the roll of a die, the outcome of a roll of a die. Random variable we could call X could only be assigned a value of like 1 or 2 or 3 or 4 or 5 or 6. They cannot be assigned like a decimal value or a fractional value. Or like the number of people in a line. It has to be either 0 people in line, 1 person in line, 2 people, 3 people, 4 people, 5 people, etc. That's called a discrete situation or a discrete random variable in those situations. A continuous random variable, on the other hand, can assume an infinite number of values on some interval between any two given values, such as if I define a random variable X to represent the weight of randomly chosen person, the weight, depending upon the accuracy of the weighing machine, could consist of many different decimal measurements. Okay. Or if I define a random variable X to be equal to a real number between like 2 and 3 on the number line, well, X can then be assigned an infinite number of fractional or decimal values. In that case, we would say that the random variable is continuous. Okay. Or if X is or represents the length of time between 2 earthquakes, again, that would be a continuous random variable in the sense that X could be assigned any decimal amount of time or fractional amount of time. So whenever we speak in terms of a continuous random variable, we're speaking in terms of the values that the variable can be assigned on some sort of an interval. And has an infinite number of possibilities. Okay. So what is a probability distribution? A probability distribution is basically a listing of the outcomes of a particular experiment, all the outcomes, along with the associated probabilities of those outcomes occurring. Okay. And a discrete probability distribution is just like any probability distribution. It consists of a listing of all the outcomes of a particular experiment with the associated probabilities for those outcomes also listed and indicated. For example, the outcome of rolling a die is either rolling a 1, 2, 3, 4, 5, or 6, and all the values are equally likely. Therefore, there are 6 values, so the probability of each outcome or each face occurring on any roll is 1/6. Okay, and therefore, if we construct this table here, where we define X, the random variable X, to be equal to the value of a face rolled on a die, then the values X can be assigned would be 1, a 2, a 3, a 4, a 5, or a 6. And then we have the associated probabilities of all those outcomes in a second row of this table, P of X. In each case, 1/6 would be the probability of any face being rolled. This table is illustrating what we call a discrete probability distribution. Okay. Notice the random variable X can only be assigned discrete values. Okay. X cannot be assigned any decimal or fractional value. And so there are a finite discrete number of values that X can be assigned. And that's why, because X is discrete, this probability distribution is a discrete distribution. Another thing I want to draw your attention to is the sum of all the probabilities of all the outcomes of the particular experiment, in this case, rolling a die, must always add up to 1. So in order to be a valid probability distribution, the probabilities, all the probabilities have to sum up to 1. If they don't, you do not have a valid probability distribution. And notice all these probabilities do add up to 1. Okay, we can also graph a discrete probability distribution. It gives us a visual rendering of such a distribution, and we can then assess the distribution for symmetry, okay, or for skewness. Suppose we have a fair coin and we toss it 3 times, and the number of heads is recorded. Specifically, we will define a random variable X to be equal to the number of heads that occur when we toss the coin 3 times. Well, X can only take on values of 0, 1, 2, or 3. And therefore, since X, the random variable X, is discrete, we will be building a discrete probability distribution. Now, we previously saw that there are 8 possible outcomes of this experiment where we flip a coin 3 times. We could flip all heads, or we could flip a head, and then a tail, or a head, then a tail, and a head, or a head, tail, tail, etc., etc. Okay, so there's 8 possible outcomes here. Now, the probability of each value of X is the number of outcomes that correspond to that value divided by the total number of outcomes of the experiment. For instance, what's the probability that X, okay, is equal to 0? In other words, what's the probability of flipping 0 heads in 3 tosses of a coin? Well, that only occurs 1 out of 8 times when we flip a tail, a tail, and a tail. So that probability of X being equal to 0 would be equal to 1/8. What's the probability of X being equal to 1, meaning we toss 1 head in 3 flips of a coin? Well, that occurs in 3 different ways. That occurs here, here, and here. So the probability, we say, of X being equal to 1, in other words, of tossing 1 head in 3 flips of a coin, is 3/8. The probability of tossing 2 heads in 3 flips of the coin, in other words, the probability of X being equal to 2, would also be 3/8. In the sense that if we flip a head, head, and then a tail, or a head, tail, and then a head, or a tail, head, head, that outcome would be experienced. So the probability of X is equal to 2 is 3/8. The probability that X is equal to 3, meaning we flip all heads, only occurs one way, head, head, head. So 1/8 is the probability that X would be equal to 3. Okay, so if I was to sum up these probabilities, they had better sum up to what? What do you think these probabilities must add up to?
1.
They have to sum up to 1, okay? And they do, and therefore we have what is called a valid probability, a discrete valid probability distribution, right? Now we can graph this distribution. The horizontal axis will represent the value that the random variable X can take on, 0, 1, 2, or 3. The vertical axis will represent the probabilities. We have our tick marks evenly spaced. The probability that X is equal to 0. The bar goes 1/8 high. The probability that X is 1, the bar goes 3/8 high, and 2, 3/8 high, and the probability X could be 3. The bar only goes 1/8 high. We can see from the graph immediately that this discrete probability distribution is perfectly symmetric. If I was to draw a vertical line right down through here, you can see that we have perfect symmetry. If you were to fold this distribution's graph about the vertical line, the bars would mesh up perfectly. Okay, so we call this a symmetric discrete probability distribution. Any questions about that? All right, so that's a discrete distribution. Another way to construct a probability distribution is from experimental data, in which case we would not use the equal likelihood model, but we would use the relative frequency model that we talked about in the past. For example, a company employs 25 people. In 1 week, 5 people made 2 sales, 11 people made 3 sales, 6 people made 4 sales, 3 people made 5 sales. We can construct this information and populate a frequency distribution table. Okay. So the frequency represents the number of people that made the respective number of sales. If we divide each of these frequencies by the total number of employees, we can calculate the empirical probabilities. Suppose we let X be defined as the number of sales made by a randomly chosen employee in a given week. So X could be equal to 2 or 3 or 4 or 5. And because X is assigned a discrete number of values, we are going to be building a discrete probability distribution. Now, what's the probability that X is equal to 2? In other words, what's the probability that we randomly select an employee and they have made 2 sales? Well, we would take the frequency 5 and divide it by the sum of all the frequencies. So 5 employees had 2 sales for the week. We divide that by 25 total employees. And so we would say that 20% of our employees experienced selling 2 things a week. So therefore, we would say the probability that X is equal to 2 would be equal to 0.20. In a similar way, 11 people sold 3 items, whatever they were. And so the probability of randomly selecting an employee and them having sold or made 3 sales in a week would be 11/25, 0.44. The probability that an employee randomly selected made 4 sales in a week would be 6 divided by 25, 0.24. And the probability, finally, that an employee randomly selected made 5 sales in a week would be 3 divided by 25, or 0.12. So these relative frequencies, we're basically passing them off to be probabilities for our situation here. Okay. And now we have a probability distribution because we have a listing of all the outcomes of our random variable and their associated probabilities. We can graph this probability distribution. Again, the horizontal axis represents the value of X, and the vertical axis represents probabilities. And you can see after graphing this discrete distribution, it does appear that this distribution is not perfectly symmetric. In fact, it would appear that this distribution is slightly skewed to the what? Skewed to the right, okay? In the sense that the bars drop off more gradually to the right of the highest bar as opposed to the left. So this is a slightly positively skewed discrete probability distribution. Any questions how we're building these discrete distributions and also graphing them? And notice the probabilities better sum up to 1. 0.2 plus 0.44 is 0.64, plus 0.24 is 0.88, plus 0.12 is 1. And again, that's always a requirement for any distribution, not only discrete, but also continuous, that the sum of all the probabilities must always be equal to 1. Okay. So these are the requirements of a valid discrete probability distribution. Number one, the sum of all the probabilities of each possible value of the random variable must be equal to 1. Number two, the probability of each possible value of the random variable must be between 0 and 1 inclusive. That's obvious since they are probabilities. We've already talked about that, the fact that you can never have a negative probability or a probability larger than 1. Another requirement for a distribution to be a valid discrete probability distribution is that let's see here. Okay, so those are the main requirements. There's two main requirements. And here's some examples here. Is this discrete distribution a valid discrete probability distribution? Well, do the probabilities sum up to 1? And the answer is no, they do not. They only add up to 70%. And so this is not a valid discrete probability distribution. How about this next one here? Is this a discrete distribution here? Well, we can see that some of the probabilities basically are violating the requirements for probabilities, namely this one. You can never have a negative probability for a particular outcome. And so therefore, this is also not a valid discrete distribution. So both of these are invalid discrete probability distributions. Okay. Okay. All right. So any questions about discrete probability distributions here so far? All right. Well, let's run off to our book and see if we can, whoops, wrong one. See if we can have a little bit of fun. So this is section 5.1. Oh, by the way, I also did post a supplemental video on Canvas where I worked through several probabilities from section 4.5. Was anybody able to access that video successfully or not? Anybody?
Yeah.
All right. I would strongly recommend, ladies and gentlemen, that you watch that video and also look through all the examples in section 4.5 and study those before you dive into the homework, and especially before you dive into the quiz. Okay. Now, another thing that just jogged my memory here. Hold on a second here. All right. Now I did open up the quiz on 4.4 and 4.5 on Alex, and I did extend the due date to the 14th midnight, the same as the due date for the chapter 4 homework, October 14th midnight. The exam, I have not opened that up yet. I'm almost done composing it, and then I will open that up. And just make sure that you do the quiz, okay, after you do the homework, and you do the exam after you do the quiz and the homework. All right. Let's see what else here. Okay. The chapter 4 exam, I may, since I'm a little late in opening it up, I may extend the due date to midnight, October 16th. I will formally send you an email confirming that and make the change on the schedule. Okay, so I do apologize not getting that open in a timely fashion. I've been really inundated here with a lot of things. Okay, so let's go to our textbook in section 5.1 and see what we can do in here. Now, there's not a lot of problems in section 5.1, but nonetheless, we will try to do some of these here. Probability distributions, discrete distributions. And again, you know, it's always wise to, you know, just look down through these examples here. Because they do give you other looks here. Okay. All right. For instance, in example 5-4 here, is a discrete valid, excuse me, is a valid discrete probability distribution? Yes or no? A here. Is that a valid discrete distribution? Well, we can see all the probabilities are definitely between 0 and 1. So, you know, that requirement is satisfied. But do these probabilities sum up to 1? All of these have to add up to 1. And let's see here, 6, 7. I think they exceed 1, don't they? I think the probability of the sum of all those probabilities is greater than 1. Is that correct? Let's see here. 4. Yeah, so it's actually 1.1, isn't it? And because of that, the sum of the probabilities is not equal to 1. And therefore, this is not a valid discrete probability distribution. How about the second one here? Is this a valid discrete probability distribution? Now, some of you might be looking at the X values up here and you say to yourself, oh, wait a minute, I see a negative value for X. Ladies and gentlemen, is that okay for X to take on a negative value? Do you think that's okay?
I think so.
Yep. A random variable can be assigned negative values along with positive values. It's just that the probabilities can never be negative, okay? Well, X is not a probability. So that's okay. Now, do these probabilities sum up to 1? Well, if you get a common denominator of 8, 1/4 is 2/8. 1/2 is 4/8. So we have 2/8 plus 4/8 is 6/8 plus 1/8 is 7/8 plus 1/8 is 8/8. And so these probabilities do sum up to 1. They all add up to 1. And they're all valid probabilities. So yes, B is a valid discrete probability distribution. How about C? Is it a valid discrete probability distribution?
Yes.
It sure looks like it. All the probabilities sum up to 1, and they are valid probabilities. That's a valid discrete distribution. How about D? Is this a discrete probability distribution? And immediately we say no, because you cannot have negative probabilities. Okay. So this is not a valid discrete probability distribution. So any questions how to identify whether or not a distribution is a valid distribution? We good on that? Okay. All right. Okay, this all right, so as I'm for classwork number 1, I want you guys to try 7 through 11. Numbers 7 through 11. I just want you to indicate whether these are or are not valid discrete probability distributions. 7 through 11. Classwork 1. Go ahead. All right, so problem 7 through 11, we're just trying to identify whether these probability distributions are valid or not. Number 7, is number 7 a valid distribution? The answer is it does not appear to be, because we have a negative what? Negative probability here, correct? Okay, so this is not a valid probability distribution because you cannot have negative probabilities. Is the second one valid? The answer again is no, you have a negative probability. Is this one valid? Well, the probabilities look okay, but do they sum up to 1? That's 0.678. Yeah, they do that up to 1. This would be a valid discrete probability distribution. Number 10, the probabilities look okay. Do they sum up to 1? This is going to be 0.55, 0.60 plus 0.40. Yes, they do. That would be a discrete, valid discrete distribution. Number 11, is it valid? Probabilities look okay, but the probabilities do not sum up to 1. In fact, they exceed 1 when you add them up. And therefore, this is not a valid probability distribution. Okay, so we all good on these type of problems here? Okay. Okay.
Yeah.
Is number 12 valid, do you think? This would be a valid probability distribution. Probabilities are okay and they add up to 1. Don't worry about the values for X or the random variable. They can be positive or negative. Probabilities cannot be negative. Okay, so keep that in mind. All right. Okay. Now, ladies and gentlemen, I want you for classwork number 2. I want you for problems 13 through 18. I want you to indicate whether a random variable associated with each of these situations would be considered to be discrete or continuous. So do problems 13 through 18. We'll call this classwork number 2. Are these discrete or continuous situations here? If you were to define a random variable for each one of these, go ahead and see if you can negotiate these. Okay, so 13 through 18, they just want us to indicate whether a random variable, which would be defined for each of these situations, would be classified as being discrete or continuous. Number 13, the number of bees that are in a hive. Do you think if I let X be equal to the number of bees in a hive, that X would take on a discrete or continuous number of values? Anybody? Number 13.
Discrete.
Yeah, discrete. There's, either one bee, two bees, three bees, 500 bees. Okay, but there's no such thing as like a decimal portion of a bee, like 1.35642 bees in a hive. That's not happening. So it's definitely discrete. Okay. How about 14? The number of boats on Lake Erie on any specific day, discrete or continuous?
Discrete.
Discrete. Yeah, there's no such thing as like three quarters of a boat or 1/10 of a boat. Well, if there is, it probably wouldn't stay afloat, that's for sure. So that's definitely discrete. There's either 5 boats on the lake, or there's 16 boats on the lake, or 200 boats on a lake on a given day. That's discrete. Number 15, the time it takes a person to drive to school, discrete or continuous?
Continuous.
Yeah, conceivably, this could take, a random variable could take on, many different decimal or fractional values of time, okay, between two given values. So I would be thinking this is more of a continuous type situation here as opposed to discrete. In other words, it's conceivable that it might take a person, maybe 15.235 minutes to get to school. Okay. So it doesn't have to be necessarily a discrete value for the time here. So that'd be continuous probably. Number 16, the temperatures on New Year's Day in the United States. Temperatures.
Continuous.
Yeah, I mean, you could have decimal temperature readings. It's possible, depending upon the accuracy of the measuring equipment. So I would probably lean towards being continuous as opposed to discrete. 17, the number of police officers in each of 10 communities, discrete or continuous?
Discrete.
Yep, discrete. Again, there's no such thing as a fractional number of police officers or a decimal number of police officers. It's either you have 5 police officers or 10 or 15. Okay, it's discrete. Number 18, the sugar content in grams in 10 cookies. Sugar content in grams.
Continuous.
Yeah, depending upon the accuracy of your weighing device, grams could be expressed to great precision with many decimals, right? So that would be probably continuous. All right, let's move on now. So I think we have a pretty good understanding as to what it means for a variable to be continuous or discrete. Okay. All right, the next question here is problem number 20. Tornadoes, the probability that there will be 0, 1, 2, 3, 4, or 5 tornadoes in a specific year is 0.3 or 0.2 or 0.1, 0.2, 0.1, 0.1, respectively. What I want you to do is I want you to build a discrete probability distribution table for number 20. And then I would like you to graph this discrete probability distribution. So 2 things. Build a table representing this discrete distribution and also graph it. So number 20 we'll call classwork number 3. Go ahead and do that there. Classwork 3. And so we're all on the same. Oh, go ahead.
Oh, I was just asking, could you scroll back up to classwork number 2? I just missed.
Number 2 was 13 through 18. We were just determining whether these are discrete or continuous.
Okay, I just had missed 18.
Oh.
Okay, thank you.
All right, number 20, for the sake of being on the same page, let's assume, ladies and gentlemen, that the random variable we're gonna use is gonna be X, okay? Although you can choose any variable for a random variable, let's use X for a random variable. Number 20, go ahead and do that. Okay, so for this problem to build a discrete probability distribution, I have a table. I have my first row labeled my random variable X, which is the number of tornadoes that could occur in a given year. 0, 1, 2, 3, 4, 5. And so we can clearly see that X is discrete. And so this distribution will be discrete. We are told that the probability of 0 tornadoes is 0.3, 1 tornado is 0.2, 2 tornadoes 0.1, etc., etc. Notice the sum of these probabilities must be equal to 1, and they do sum up to 1. Now we can graph this discrete distribution. The horizontal axis is the value that X can assume, and I evenly spaced my tick marks. You don't have to have 0 start here at the origin. You can put it out here. The vertical axis represents probabilities. And basically, the height of your bar is going to be equal to the probability of X assuming a particular value. So probability that X is equal to 0, the bar would go 0.3 high. Probability X is equal to 1, bar goes 0.2 high. Probability that we have 2 tornadoes, the bar goes only 0.1 high, etc., etc. After graphing this distribution, you can see that it is not symmetric. If anything, it looks like it's grossly positively skewed. So it looks like this distribution, in a sense, is positively skewed, okay? But it is not symmetric. All right. Any questions about how we put together that table and graph that discrete probability distribution there? Okay, and a graph is nice because you can tell basically very quickly what the most probable value of that X can assume. We can see that X being equal to 0 is the most probabilistic value, just by looking at the height of the bar. So graphs are very useful in helping us cut through the chase and trying to understand what data is trying to tell us. All right, one more classwork out of here, and then we will move onward. Let's move on down to this hockey problem number 29. We'll call this classwork number 4 here. Again, I want you to build a discrete probability distribution for this situation and also graph it, okay? Go ahead. Now, and again, we'll use X for a discrete random variable. And these probabilities, ladies and gentlemen, are not as nice as the probabilities in the previous problem. So you're going to have to become a little bit more imaginative as to how you develop your tick marks on your vertical axis, okay? But I'm going to let you think about that and come up with something with that. All right, so go ahead and do that. Classwork number 4. All right, so this is the discrete probability distribution that we can construct from this hockey problem where X represents the number of goals that a hockey team scores. And P of X is the probability of that occurring. Now, as far as the sum of these probabilities is concerned, they should add up to 1, technically speaking. Sometimes when you're working with decimals like this, that you take them out to 3 decimal places, there might be some slight round off difference, okay? That is usually considered to be negligible in a situation like this where we're carrying these out to the thousands place here. But the sum should be fairly close to 1, all right? If it's way off from 1, then there is a problem, okay? All right, now here is the graph of this discrete distribution. My horizontal axis is the value of the random variable x-axis, and the vertical axis is the probability of x assuming these values. I chose to space my tick marks on my vertical axis by 1/10 of a unit apart, or 100 thousandths of units apart. 0.100, 0.200, 0.300, 0.400. And then my bars went approximately as high as these probabilities indicate. All right, so it is kind of an approximation as far as the exact height of these bars is concerned, because some of these probabilities are kind of messy and fall kind of in between 2 of these tick mark values here. So just do the best you can. You know, as long as you're, approximately in a neighborhood, you're going to ascertain the same information about this distribution that the graph is trying to tell us. And it looks like this discrete distribution it appears to be somewhat negatively skewed as the classes fall off more gradually to the left of the high class as opposed to the right, where there's an abrupt drop here, okay? All right, so hopefully this section has shown us how to differentiate between a continuous and discrete random variable, and how to identify whether a discrete distribution is valid or not, and also how to construct a discrete probability distribution and also graph it, okay? All right, so that brings to a conclusion this section here, 5.1. Now we do have some extra time, so I'm going to begin the next section, 5.2. I do not intend on finishing the entire section 5.2 today, but I would like to at least begin it. So this is entitled The Mean, the Variance, and Standard Deviation and Expectation of a Discrete Probability Distribution here. Okay. So by the time we do get done with this section, we will be able to compute the mean and the variance and standard deviation, and also work with what is called an expected value for a discrete random variable. And expectation can also be used to deal with real life situations, as we'll find out. All right, the mean of a sample or population, of course, is the sum of all the data values divided by the total number of data values. Suppose we flip a coin twice and count a number of heads. We specifically will let X be equal to the total number of heads that occur. There are therefore 4 possible outcomes: head, 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 tail, tail, head, or tail, tail. This corresponds to X being assigned values of either 2 heads, 1 head, or 0 heads. Now, what would be the mean of tossing 2 heads, 1 head, 1 head, or 0 heads? Well, if you added these together and divided by 4, you would think the mean would be 1, okay? In this list of values, 2 occurs once, 1 occurs twice, 0 occurs once. And the mean, the way we computed it, 2 plus 1 plus 1 plus 0 divided by 4, could also be computed by taking the value of the random variable X and multiplying it by its weight. And its weight of occurrence would be the probability of X taking on that value. For instance, what's the probability of flipping 2 heads? Well, that occurs 1 out of 4 ways. So that probability would be 1/4. What's the probability of flipping one head? Well, that occurs 2 out of 4 ways. So 2/4 is its probability. The probability of tossing 0 heads only occurs 1 out of 4 ways. 1 out of 4 ways here. On this handout here, they got 0 times. So then they take the value of X and multiply it by the associated probability. So 2 times 1/4 plus 1 times 2/4 plus 0 times, that should be 0 times 1/4, as the probability of flipping 0 heads is 1 out of 4, not 1/2. So there's a typo on this little PowerPoint here. Now, if you multiply and add all these up, notice you are going to get 1, which is the exact same value that we got when adding 2 plus 1 plus 1 plus 0 divided by 4. Okay. Therefore, the mean, denoted as mu, notice they're using this symbol. Looks like a U, but actually it comes from the Greek alphabet. It's called mu. And mu is used to represent the mean of a population. We've discovered that in the past. Or it's also used to represent the mean of a discrete probability distribution. And ladies and gentlemen, to determine the mean of a discrete probability distribution is pretty simple. All you do is you basically sum up the products of the value that X can assume times its associated probability. We have another name for the mean of a discrete probability distribution. It's called the expected value of the random variable, the expected value. In the sense that if we were to continue to perform this experiment over many trials, okay, we would expect the random variable X to take on the mean value of this discrete distribution. Okay, so that's why they got the letter E here. That represents the word expected. So E of X, when you see this notation, you should interpret it as the expected value of the random variable X. And notice that, again, that's going to be the sum of the values that X can take on times their associated probabilities. So, ladies and gentlemen, the probabilities are actually the weights. So this is a weighted average or a weighted mean, if you will, because these probabilities are not always necessarily going to be the same. That's why we call it a weighted average, all right? In much the same way that we would compute a grade point average after a semester. Okay. The idea of expected value comes from gambling. For example, the expected value of playing a game of chance is the amount of money on average that you will gain or lose per play. And this is assuming, the key here is that this is assuming that you continue to play the game for a large number of times or trials, all right? For instance, suppose we had an unfair coin in the sense that the probability of tossing a head or a tail is not exactly 50-50. Well, if I toss this unfair coin 10 times and, you know, keep track of the number of heads that I toss in 10 trials, I get a relative frequency, okay? But ladies and gentlemen, if I toss this coin 100 million times, the same unfair coin 100 million times, then the relative frequency of the number of heads that occur in 100 million trials, okay, is going to be extremely close to the actual probability of a head occurring on any given flip of this unfair or biased coin. Okay, so that's the idea by what we call the expected value of a random variable is it is the value that the random variable on average would take on, provided that we undertake or exercise many trials of a particular experiment, okay? And this in part is made possible by the law of large numbers that we've seen in the past. where we've seen that relative frequencies always approach true probabilities, provided that the number of trials of the experiment approach infinity. Okay. All right. So this goes back to the previous presentation where we tossed a coin 3 times, and we seen that in doing so there were 8 possible outcomes. And suppose we let X be a random variable, which is equal to the number of heads that occurs when we toss a coin 3 times. And therefore, X can take on the values of 0, 1, 2, or 3. In other words, we could toss 0 heads, or 1 head, or 2 heads, or 3 heads when we toss a coin 3 times. The next row, of course, are the associated probabilities that we've seen in the past. And we've seen how we computed these probabilities based on all the possible outcomes of this experiment. Notice again that these probabilities sum up to 1. Suppose we form another row on our table, which is X times P of X. So we take the value of X and multiply it by its probability of occurrence. And so, in other words, how did they get to 0 here? They got to 0 by multiplying 0 times 1/8. How did they get this 3/8 here? They got that by taking X equals 1 and multiplying it by the probability of X being equal to 1. In other words, they got that by taking 1 times 3/8. 6/8 is obtained by taking 2 times 3/8. And 3/8 is obtained by taking 3 times 1/8. Okay, now if we take this last row and we sum up this last row, we compute what is called the mean of this discrete probability distribution. That is to say, we compute, okay, the expected value that the random variable X would assume, okay, on average, if we conduct this experiment many times. And ladies and gentlemen, after adding all of these fractions together and then converting it into a decimal, we see that the expected value of our random variable, when we flip a coin 3 times, we would expect that random variable, which is defined to be the number of heads that occur, to be equal to about 1.5. So how can we, kind of like explain what that is saying? Well, on average, we would expect our random variable X to be equal to about 1.5. Now, remember, X represented the number of heads that occurred when we flip our coin 3 times. So from a practical standpoint, that doesn't make any sense to say that the expected value of a random variable is 1.5, because obviously you cannot toss 1.5 heads, okay? But for purposes of like gambling games, all right, let's say that you win a prize if you flip so many heads, okay? So we can use this expected value of a random variable to basically give us a determination as to how much you would expect to win or lose in such a game, where the prize you win depends upon the number of heads that you toss when you toss a coin 3 times. And we'll see this play out with what are called expectation word problems a little later on. Probably not today, but when we continue or finish this lecture next week, we'll see how that plays out there. But again, the expected value of X is about 1.5. So in other words, if you were to flip this coin 3 times for, let's say, 100 million trials, 100 million times, which is a large number of trials, obviously. And on each trial, if you kept track of the number of heads that occurred, if you were to find then the average number of heads that occurred through those 100 million trials, okay, you would find that average to be very close to 1.5, okay? That's what that's saying. All right, so again, expected value is found by taking the sum of the product of X's value times its associated probability. Any questions about how we found the mean of this distribution 1.5 here? Now, I think we graphed, didn't we graph this one, this distribution? Let me double check here. I want to show you something on the graph, but I got to go back to the previous presentation though. Okay, let me go back to the previous presentation. And okay, right here. So when we flip the coin 3 times, I think we did graph it, and there it is right there. Okay. So ladies and gentlemen, we can see that the mean of this discrete distribution, the expected value of the random variable X, is that over the long haul of flipping this coin 3 times, we would expect X to take on average, we would expect X's value to be 1.5. And you can see that 1.5 definitely is dead center in this distribution. See it right there, 1.5. That would be the expected value of our random variable X, 1.5. That is called the mean of this discrete probability distribution. So it does make sense when you look at the graph here, why the expected value would be 1.5. Okay. All right, let's go back here. Okay, so let's go now to our textbook and see if we can maybe do a couple problems with the expected value. So this is going to be in section 5.2 here. And as always, you know, it's wise to kind of look over the sections that are being covered here. All right, here's another example of computing an expected value. We can walk through this example. It says, find the mean of the number of spots that appear when a die is tossed. Of course, X, we can define X, the random variable, to be the number of spots that occur in any given toss, which means X takes on a value of 1, 2, 3, 4, 5, or 6. And the associated probabilities, assuming it's a fair die, would be 1/6 for each of those outcomes. Okay. Now to compute the expected value of the random variable X, ladies and gentlemen, we would use our formula. We would take the sum wait a minute here. This is not right. In your textbook here, oh, okay, I see what it's saying. It's saying we would sum up the products of X and its associated probability. They should have put that seriously inside parentheses, because you know what? Without the parentheses, you know how I interpreted that? I interpreted this as the sum of X. In other words, adding up X first and then multiplying by the probability. Although, you know what? That would be the same thing here, because all these probabilities are what? Why would that be the same thing here in this case? Even though they didn't put parentheses around the X and the P of X. Why would it work out okay here?
Because it's 1.
Well, because all the probabilities are the same. Do you agree? In other words, all these outcomes are equally weighted, correct? 1/6, 1/6, 1/6, 1/6. But is that always going to be the case in a discrete distribution? Are all the probabilities for outcomes going to always be the same? The answer is obviously what? Not. So they should have been a little bit, maybe a little more careful here in the textbook. It works okay for this one to sum up the X's first and then multiply by 1/6, because that's equivalent to as if I factored 1/6 out of each of these terms, correct? then it would be 1/6 times the sum of 1 plus 2, 3, 4, 5, and 6. So it works okay here because these probabilities are all the same. But usually they're not. For that reason, they really should have been a little more accurate in a textbook and put this inside what? Parentheses. Which means you really should multiply x's value by its probability first and then summed up all the values. Okay. Anyways, when we go through the arithmetic here, we do get 21/6, which is 3.5 or 3.5. And that makes sense because you can see that 3.5 is the middle, literally the middle of x's values. Do you agree? So that is the mean or the expected value that we would expect x to take on over the long haul of this game of tossing a die. So if I toss this die maybe 1 trillion times, okay, I would expect on average x's value to be 3.5. Now, don't get me wrong, in a practical sense, there's no such way of x actually taking on 3.5 dots, okay? This is an average, ladies and gentlemen, and it's over the long haul of playing this game here, and the game is tossing a die, all right? Okay, so does that make sense how they computed the expected value or the mean? And again, they really should have parentheses around here because these probabilities are usually not the same. For this one it is, but that's usually not the case. So careful on that. All righty. Let's see what else we got here. All right, here's an interesting one. A very old water system in a manufacturing plant has 4 independent valves. Now, to say the valves are independent of each other is to say that what you do with one valve in no way, shape, or form affects the probability of what's going to happen when you fiddle around with the other valves. These are independent valves here. Right? All right, so we have 4 independent valves that have a 50% chance of working correctly over a year. The valves are checked yearly to make sure that a valve is either bad or good. Find the mean number of good valves in the system. Okay. So we have 4 valves and each one can, either be in a state of good or in a state of functional operation or non-functional operation. All right. So how many different outcomes can we have here if each valve can take on one of 2 states, either good or bad? Well, that's going to be basically 2 to the what? 4th power. Do you agree? Which is 16 possible outcomes. In other words, it could be the case that all 4 valves are bad right here. Or it could be the case that the first three valves are good, but the first 3 valves are bad, but the last valve is good. Or it could be the case that all 4 valves are good. So there's 16 possible different states that all these valves could be in, okay? A tree diagram could have also helped us to enumerate these possibilities here, although a tree diagram does take up some serious space. All right, ladies and gentlemen, let's build a discrete probability distribution where X represents the number of good valves. So obviously X can take on the values of 0, 1, 2, 3, or 4, where no valves are good, 1 valve is good, 2 valves are good, or 3 valves are good, or all 4 valves are good. And the associated probabilities then would be computed by looking at the relative frequency of occurrence out of 16. In other words, what's the probability that all valves will be bad? That only occurs 1 out of 16 ways. So that's why its probability is 1/16 here. What's the probability that we have 1 good valve? Well, 1 good valve occurs how many ways out of 16? That occurs here. 1 good valve occurs here. And where else? 1 good valve right here. And right here. So having 1 good valve occurs 4 out of 16 ways. 2 good valves occur out of 6 out of 16 ways. 3 good valves is 4 out of 16. And 1 good valve occurs 1 out of excuse me, for good valves occurs 1 out of 16 ways right here. Okay, so we understand how we got these probabilities assigned here. Notice these probabilities do add up to 16/16 or 1. And suppose now we want to compute the expected value of our random variable. So how would we do that? Well, we've seen that the formula to do so is the sum of the products of X and its associated probability. Okay. That's how we're going to compute the expected value. So we would have another row in this table, which would be the X times P of X row. And 0 times 1/16 would be 0 here. 1 times 4/16 would be 4/16. 2 times 6/16 would be 12/16. 3 times 4/16 would be 12/16. And 4 times 1/16 would be 4/16. And if you add these all together, you will generate the mean of this discrete distribution or the expected value of the associated random variable. Okay. And so therefore, you can see that the mean of this discrete probability distribution or the expected value of the random variable X is going to be equal to 2. Now, this is a case where the author really got sloppy because look at these probabilities are not the same here, ladies and gentlemen. They're all different. And all the more reason why they really should have used what? Parentheses here. They should have enclosed it inside parentheses. That's critical. Because if you don't include that inside parentheses, then it looks like they summed up all the X values first and just multiplied it by some probability. Well, what probability would that be? All the probabilities are different. So you should use parentheses there. Just make a note of that, maybe change that in your book. All right, so the expected value is 2. And so, ladies and gentlemen, over the long haul of this valve system at this manufacturing plant, on average, we would expect how many valves to be good on average over many years on average? We would expect 2 valves to be good and 2 valves to be bad, correct? All righty, that's called the expected value or the mean of this discrete distribution. And you can see that 2 definitely is dead center right in the middle here. You can see that we have a perfectly symmetric distribution too, because this is the most frequently occurring value for X. And to the left, these probabilities drop off with equal frequency, 4/16, 4/16 to the right, 1/16 here to the left, 1/16 here to the right. We have a perfectly symmetric distribution there. Okay, we already seen that one there. All right, it goes back to, you remember the number of employees that had so many sales in a week? Remember we looked at that discrete distribution where the probability of randomly selecting an employee and them having 2 sales in a week would be about a 20% chance. Okay. Well, what would be the expected value of X for this distribution? Well, it's going to be the sum of 2 times 0.2 and 3 times 0.44 and 4 times 0.24 and 5 times 0.12, in which case we get 3.28 as the expected value for a random variable. So on average, if we kept these employees for many years, and we kept track each week of the number of sales that each employee has, we would expect, ladies and gentlemen, on average, there to be, we would expect on average for any employee, that works for us to have on average of about 3.28 sales per week. This is on average. So you got to understand this is an average, and that's why it's not exactly, 2 or 3 or 4 or 5. Because from a realistic standpoint, there's no such thing as having 3.28 sales per week. I understand that, but this is called an average, a weighted average. Okay. So this is still nonetheless instructive because it indicates to us that during any given week, on average, any given employee will have about 3 sales, 3 to maybe 4 sales a week. Okay. All right, and then we will also look next week at how to compute the variance and standard deviation of a discrete probability distribution, but we're not going to do that today. Let's go down and see if we can do maybe a problem or two with expected values. Okay. So number 2 here, we'll call that classwork number, I forgot. Well, maybe classwork number 4 or something. Again, it doesn't really matter what we call the classworks, whether it's 1, 2, 3, 4, 5, 6, 7, or gazillion, doesn't matter. We basically send them all in anyways, okay? What I want you to do for this problem is I just want you to compute the mean of this discrete probability distribution. Do not compute the variance and standard deviation, just the mean. All right, go ahead and do so. Compute the mean or the expected value of our random variable x. What does this even pertain to? Well, this pertains to the number of fish caught per day at yield fishing hole. And P of X is the probability of catching this number of fish on a given day. So that is a valid discrete probability distribution. I want you to find the expected value for the random variable X. All right, go ahead and do that. We'll call that classwork number 4. Okay, so to compute the expected value of this random variable here, we take the value that X can assume and multiply it by its associated probability. And then we add all these products up. So 0 times 0.24 plus 1 times 0.36 plus 2 times 2700s plus 3 times 800s plus 4 times 300s and 5 times 200s. Add all these up and you get 1.36. So can anybody explain or basically indicate for the rest of us, what is that really saying? So what is that really saying in the context of this problem? At 1.36, what does that really mean? What does that really mean?
The average amount of fish caught.
Okay, that would be, you are correct. The average amount of fish that we would expect, that's the key word, that we would expect to catch on any given what day. Do you agree if we come to the same place, right? Now, that's an average. You're not going to catch exactly 1.36 fish. That's just an average. All right. And I have a question for you. Why is that average so darn low here? Because in reality, some people are catching 5 fish here in this hole. Well, ladies and gentlemen, you got to look at the weights. The weights are the probabilities here. And you can see that the probability of catching 5 fish at this place is slim. It's only like what, a 2% chance, correct? You can see that most of the weight, okay, is down here for 0, x equals 0 and x equals 1. So if you look at that from that perspective, it makes sense that the mean is pushed way over here to the left, only being about 1.36, which is about somewhere right in here, right? So it's really the weights and the probabilities that in large part determine the expected value of a random variable. Now, next week, when we get into looking at the variance and standard deviation of these distributions, that'll give us some sort of an idea as to some sort of an interval that we would expect to have X lie in, okay, over the long haul here. All right. So this is an interesting situation down here. It's called Benford's Law. And Benford's Law, ladies and gentlemen, is actually used to basically catch criminals. That's right. Benford's Law is used to catch people that write fake checks. Okay. At least it was used in the past. There's not too much check writing these days. But Benford's Law, according to this law, it's really amazing here, but it says the leading digits in actual data, such as stock prices, population numbers, death rates, lengths of rivers, or maybe like the first digit that's written for a check number, okay, do not occur randomly, as we would, guess. But instead, they follow a distribution according to Benford's Law. Below is a probability distribution for the leading digits in real-life lists of data. I don't know what the data is, but they want us to compute the mean for this distribution here. So we do have a valid discrete probability distribution, and they want us to compute the average or the mean here. And so what you're going to do is you're going to take care of this here. Now, ladies and gentlemen, I'm going to show you on our TI-84 how we can maybe speed this up a little bit here. So let's try to find the expected value of this random variable for Benford's Law using the calculator. So we'll go to Stat, Edit, and in list 1, I'm going to type in the values for X. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And in list 2, I'm going to type in the associated probabilities. Okay. we may revisit this law a little bit later on. And I can show you what I was talking about too. They use this law to help detect fraud with check writing. But again, there's not too much check writing that's done in these days. At least I used to have a checkbook. That was a long time ago. I no longer write checks. And does anybody write checks still? Just curious. Anybody? Is that still? I mean, I haven't written a check in a long time. I'm just wondering if that's still is that still an option out there? Writing a check?
Yeah, some places still take checks or
Oh.
require you to do something like that.
All right. Yeah, I like I said, I haven't done so in a long time, so I'm totally out of tune with that. All right, anyway, so we put X's value in list 1 and we put the associated probabilities in list 2. And we can speed this up. So let's go to list 3, put our cursor up on the name of list 3. And in list 3, what I'm going to do is I'm going to tell my calculator to take list 1. So second 1. And I'm going to have it multiplied by list 2. Second 2. Everybody see that there? With my cursor on the name of list 3. I typed in list 1 times list 2. And to get the name of the list, of course, you have to precede the 1, 2, 3, 4, 5, 6 buttons with the second key to bring up the appropriate name of the list. Hit enter and boom, that list is populated with the products of the numbers in list 1 and 2. Now all we have to do is just sum up list 3 and we'll have the expected value. Well, instead of doing this manually and killing a lot of valuable time, we can just go to stat, calculate 1 var stats for list 3. Hit enter, and boom, the sum of the X values is the sum of the values in list 3. So there's your expected value for X, 3.441. That's your expected value. That's the mean of this discrete distribution, 3.441. Everybody see that there? 3.441 would be the expected value or the mean of this distribution. And you can see that if you kind of like pay attention to the weights or the probabilities here, you can kind of see that, yeah, it kind of seems like maybe that makes sense where the mean would be kind of like somewhere in here, because look at all these load numbers have very large probabilities, relatively speaking. You get up here to high numbers here and the probabilities drop off markedly, okay? So that would be the mean or the expected value of a random variable X. So we would expect on average X to take on a value of about 3.44, okay, on average. All right. So any questions how we're computing the expected value or the mean of a discrete probability distribution? All right, maybe one more here, ladies and gentlemen, and please use your calculator for number 6 here. This is not a classwork. I just want you to try this on your calculator. Do number 6. The county highway department recorded the following probabilities for the number of accidents per day on a given stretch of freeway in 1 month. The number of accidents per day and their corresponding probabilities are shown. Find the mean. I just want you to compute the mean. So go ahead, find the expected number of accidents that we would, you know, have to fathom here on this stretch of highway for 1 month. Use your calculator to do that. Just make sure you can do this on your calculator. That's what I'm really going after here, okay? So let's see if we can use our shortcut. Bring up our machine.
2 seconds.
Okay.
I just helped myself. Doing it best time.
All right. Now we're going to go to stat, edit. And we're going to clear out the list here. Okay. Better clear out list 3 too. All right. So in list 1, we just type 0, 1, 2, 3, 4. Okay. Type in the associated probabilities in list 2. Make sure you keep the probabilities paired with the value of X. That's very important. Otherwise, this is all in vain. All right, now we just have to move our cursor up on the name of list 3 and say let list 3 be equal to list 1 times list 2. List 1 times list 2. And now we just sum up list 3 and we have the expected value of X. To do that, you just go to stat, calculate 1 var stats for list 3. And your answer is the sum of the X values, 1.3. So there you go. That would be the expected number of accidents to have on this freeway for any given month. On average, we would expect about 1.3 accidents. Okay, about 1.3 accidents here. So about 1 accident, all right, per month, based on the data that was collected and the observations over, I would imagine, a fair amount of time to generate these probabilities of accidents for this particular stretch of freeway here. Okay. All right, ladies and gentlemen, that's it for today. So we looked at discrete distributions and we learned how to find the mean or the expected value of such a distribution. Next week, we'll look at the standard deviation and variance and also work with expectation problems. All right, so again, I will make available the exam. I will probably extend the due date by 1 day. And I will send a formal email. So just be in the habit of checking your email at least once a day. It's a wise thing to do. And because oftentimes I send out important information for the whole course. All right, I'll be on the line for a couple minutes if you have any questions or concerns. If not, have a great weekend.
Have a good weekend.
I have a question. In order to go back over like our quizzes, we'll have to schedule an office hour so like you could open up and we could go back and see which ones that we missed for like the questions and everything.
Now you get 2 takes on the quizzes. So and I think I geared it so that it's a quick retake, correct? So that like, you know, if you only have to do
Yes.
the ones that you missed, correct? You don't have to redo the ones you got correct. That's called a quick
Yes,
retake.
that's correct. Yes, I was saying for like after we take the like if we do take the 2 attempts and after we complete that and we want to go back over to see like which questions we didn't get right, we'll have to schedule with you to go over the quiz so like so we can see it.
Yeah, you could do that. I mean, you don't have to, you know, make a formal schedule. We could maybe do that after class sometime, you know. I usually have a
Oh,
little bit
okay.
of class
Okay.
to
I was just
run through.
wondering because I was trying to like just go over the quiz after I had taken it, but I wasn't able to see the questions. I think because it just didn't give me like the access to go back and
Go back and what, look at them or something? Or
I'm sorry, yeah, it didn't give me the option to go back and review like after the quiz was taken.
Now, when you do like the homework assignments, it does give you that option, I believe. Is that correct? To look at
Yes, that's correct. We can always
fine.
go back to the homework.
So that's a good thing for homework, that it does do that. For the quizzes
Okay.
and the exam, I'll have to double check that, but I don't think it does afford you that option for exams and quizzes to do that.
Okay.
But if you wanted to do that, like, you know, after class sometime, we could kind of like go back through and run through some of the problems or whatever that you wanted to
Okay,
see.
thank you.
Okay. Yeah.
All right.